most difficult to solve problems in mathematics. Let's start with the standard formulation of the Collatz conjecture. Take any positive integer. If the number is even, divide it by 2. If it's odd, multiply it by 3 and add 1. Now repeat this process with the new number. The conjecture states that no matter what number you start with, you'll eventually reach 1, after which you'll enter the cycle. 1 for 2, 1, and so on forever. Let's see an example. If we start with the number 7, since 7 is odd, we apply the rule 3n plus 1. So we get 3 times 7 plus 1, which is 22. 22 is even, so we divide by 2 and get 11. 11 is odd, so we get 3 times 11 plus 1, which is 34. 34 is even, so we divide by 2 and get 17. 17 is odd, so we multiply by 3 and add 1, getting 52. 52 is even, so we divide by 2 and get 26. This sequence continues. 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, and finally 1. A common way to visualize the Collatz conjecture is to plot the trajectory of different starting numbers. Here we see a plot showing several trajectories, with the vertical axis representing the value and the horizontal axis representing the number of steps. These spikes and drops are why the Collatz sequences are sometimes called hailstone sequences. They rise and fall unpredictably like hailstones in a cloud. The recent research paper by Sakinen proposes an interesting approach to the Collatz conjecture. Instead of looking at individual steps, the paper considers accelerated blocks that compress sequences of operations. Specifically, instead of performing the 3x plus 1 operation followed by divisions by 2, we can combine them into what's called an accelerated block, represented as 3x plus 1 divided by 2. The key innovation in the paper is what's called a mirror-modular spine approach. By tracking residues modulo 3, the author discovers an interesting pattern. Every rise in the sequence ends with a residue of plus 2, which is congruent to negative 1 modulo 3. Then, after the first division by 2, this flips to a residue of plus 1 modulo 3. This creates an alternating pattern between plus 1 and plus 2, forming what the paper calls the mod 3 backbone, or spine of the sequence. The paper introduces 2 key parameters for each accelerated block, n and m. The parameter n is what's called the dyadic depth of b plus 1, meaning the highest power of 2 that divides b plus 1. The parameter m is the highest power of 2 that divides the rising value r. Using these parameters, we can track the transformation from one odd number to the next in the Collatz sequence. One of the key insights in the paper is about primitive primes. For every rising block with exponent n, there exists a primitive prime p that divides 3 to the n minus 1. By primitive, we mean a prime factor that doesn't divide 3 to the k minus 1 for any smaller k. The crucial observation is that since descents only divide by powers of 2, these primitive prime factors persist forever in the sequence. This is a powerful result because it means no non-trivial cycle can exist. Why? Because each cycle would accumulate an infinite collection of primitive primes, which is impossible for a finite-length cycle. To prove that sequences are bounded, the paper introduces a Lyapunov function. The function f, x, equals log base 2 of x. For a block with parameters n and m, the height multiplier lambda equals 3 to the n divided by 2 to the n plus m. The key insight is that this multiplier, on average, creates a negative drift. In particular, descents occur infinitely often, and each extra factor of 3 further reduces the height multiplier, ensuring all trajectories remain bounded. Since no non-trivial cycle can exist, and all trajectories remain bounded, this means every positive integer must eventually reach 1, proving the Collatz conjecture. Interestingly, the paper also discusses why this approach works specifically for the 3x plus 1 problem, but fails for similar variants like the 3x minus 1 problem. These are called sister chains, and they don't exhibit the same mirror-modular spine property that makes this proof work. To summarize, the paper presents a novel approach to proving the Collatz conjecture using a mirror-modular spine structure and accelerated blocks. The proof has 2 main components. First, proving that no non-trivial cycle can exist due to the accumulation of primitive primes. Second, showing that all trajectories remain bounded due to a negative Lyapunov drift. If confirmed, this would solve one of the most famous open problems in mathematics,